In this section, we're going to look at calculations of pH of weak acids. Previously, we looked at strong acids and strong base calculations of pH. Now we're going to look at weak acids. So for a weak acid, we're going to have to look at the equilibrium constant for that acid. Strong acids, there is no equilibrium. They ionize completely. For weak acids, there is an equilibrium. So in this reaction, we have our generic acid, HA, where H is the proton that I can donate. It reacts with water to form the conjugate base and hydronium, the conjugate acid. So the equilibrium expression would be, for this reaction, right, we ignore water. So it'd be, what's the concentration of my conjugate base times the concentration of hydronium all over the concentration of my weak acid, HA. And this is known as our acid dissociation constant, or Ka. Right? I said this semester we look at Ka, we'll look at Kb, Kc, Kp. All of these equilibrium expressions are the same thing, except we're just talking about this with respect to acid dissociation constant, hence the Ka. It's always going to be products over reactants, right? So that's what we're looking at right here. I've got my products, the conjugate base and the conjugate acid as my products, all over the initial concentration of my weak acid, HA. So I have a question for you. So what is the relationship between the magnitude of Ka and the strength of the acid? So the answer to that question is, right, stronger acids have larger values of Ka, larger Ka values. Right, that makes sense because a stronger acid, that means it's going to dissociate farther. That means I'm going to have a larger concentration of the conjugate base, a larger concentration of hydronium, and that's what I'm measuring as a marker of my pH. So if I have a higher concentration of products, right, these numbers are going to get larger, these numbers are going to get larger concentration of products at the expense of my reactants. So a smaller concentration of my reactants. So large numerator, small denominator, a large value of Ka. So the stronger the acid, the larger the value of Ka. The weaker the acid, the smaller the value of Ka, because that means I'm going to have a smaller concentration of products at equilibrium and a larger concentration of reactants. And here are some examples of that. So HF, hydrofluoric acid, is a weak acid. It has a Ka of 6.8 times 10 to the minus 4. Nitrous, benzoic acid, here's the acetic acid that we talked about before, Ka of 1.8 times 10 to the minus 5. All of these are very small Kas, but we can compare these Kas amongst all the values here to see that of these weak acids listed, right, the largest value of Ka is with hydrofluoric acid. So of the acids listed, that would be the strongest acid in this series because it has the largest value of Ka. Another important relationship to remember is that as the Ka decreases, right, so the acids are getting weaker and weaker and weaker. That means the equilibrium is shifting farther and farther and farther to the left, and they're doing that because the conjugate base, the strength of the conjugate base is increasing. So as Ka decreases, the strength of the conjugate base increases. Right? And that's why it's a weaker and weaker acid, because it's got a stronger and stronger and stronger conjugate base, pushing the equilibrium farther and farther to the left, farther and farther to the starting material, the original acid we put in solution. Okay, so here's a question. Let's think about how we calculate equilibrium and now bring in some pH calculations as well. So I have a 0.1 molar solution of formic acid. Formic acid is a weak acid. And that solution has a pH of 2.38. Calculate the Ka of formic acid at this temperature, right? So let's think about that. We know the generic reaction, right? Here's formic acid. It reacts with water to form formate. the conjugate base, and hydronium, the conjugate acid. And we know, the only other value we know is the initial concentration of formic acid. Well, we actually know more than that as well, right? We know in this Ka, what are some of these values that we know? Right, we know our concentration of our acid, our formic acid. We want to find Ka. Well, to find Ka, we need to figure out what is hydronium and what is the concentration of the conjugate base. And whether you know it or not, we actually have those numbers. We actually can find the concentration of hydronium and the concentration of the conjugate base. Right, so let's take a look at that equilibrium again. It's the concentration of hydronium times the concentration of formate all over the concentration of formic acid. So we know this right now, and we want to find Ka. We do not know our hydronium or our formate concentration, but we do know pH. And remember, pH, right, we can find hydronium concentration from pH. So let's do that. Right, hydronium concentration, remember that's one of our variables, equals 10 to the negative pH. So hydronium concentration equals 10 to the negative 2.38. My hydronium concentration equals 0.0042 molar. Okay, now I've got one less unknown because now I know the concentration of hydronium in this solution based on the pH, right? The pH tells me the concentration of hydronium. I also know the concentration of formate. How can I determine the concentration of formate in this reaction? If I look at the stoichiometry, for every 1 molecule of formic acid that goes into solution, I get 1 molecule of formate and 1 molecule of hydronium. So that means formate and hydronium are going to be made in equal numbers, and they will have equal concentration. So because I know the pH and I know hydronium concentration, I also know the concentration of formate in solution. Both of those concentrations are identical because they both come from the same source. They both come from formic acid. So if 1 molar formic acid ionized, I would have 1 molar formate, 1 molar hydronium. If 0.0042 molar formic acid ionized, well, then I'm going to have 0.0042 molar hydronium and formate in solution. And that's what I see. Because I know one, I immediately know the other one because of the stoichiometry of the balanced chemical equation. So now we can set up an ice table to determine our equilibrium concentrations of everything in the solution before we calculate the Ka of this acid. So we determined that I start with 0 concentration of hydronium, 0 concentration of formate, and we determined that at the end, right, we had 0.0042 molar of both of those based on the pH of the solution, right? So that means the change here was 0.0042, 0.0042, and that would also be the change in the concentration of our weak acid, formic acid. But we have one way to simplify these calculations. Because this change in concentration is so small, because this is a weak acid, that change in concentration is small enough that we can ignore that change in concentration and just essentially say that the initial concentration is going to be equal to the equilibrium concentration because only a small amount of that acid actually ionized. So the concentration is pretty close to the initial concentration that we started at. And that'll make our calculations a little bit easier, and this assumption is safe because of the difference in magnitude of the concentrations we're comparing. So here's our calculation for Ka. We now know our formic acid concentration, our hydronium concentration, and the concentration of the conjugate base, the formate. So we have our Ka. We can plug everything in to the expression that we already determined. right? 0.0042 is the concentration of hydronium times 0.0042, which is the concentration of formate, divided by the concentration of formic acid, which is 0.1. So multiply those two and divide, I get a Ka of formic acid that's approximately 1.8 times 10 to the minus 4. Right, so that value is much less than 1, so that means, right, this is not a strong acid. It only partially ionizes in solution. And that's what we see. I've got 0.1 molar in solution. I only have 0.0042 molar that actually ionized into that solution. So a calculation you should be able to do, you should be able to go from pH to Ka for an acid or for a base. And just to confirm that it's a weak acid, we can also calculate the percent ionization, where percent ionization is essentially how much of that acid ionized, so how much hydronium do we have in solution, divided by what was the initial concentration of acid that I added to the solution, multiply that by 100 to turn it into a percentage. So the percent ionization of formic acid would look like this. We calculated the concentration of hydronium to be 0.0042 molar. The concentration of the initial acid is 0.1 molar. Right, here's how much ionized. Here was the total amount we had in the solution. Multiply that by 100 to confirm that yes, this is a weak acid because only 4.2% of that acid ionized. So if I put 100 molecules of this in solution, right, 96 would stay as formic acid in solution, and 4 of those molecules would actually ionize into hydronium and formate. So here's the other version of that calculation. We calculated Ka from pH. You should also be able to do the opposite of that calculation. You should also be able to calculate pH from Ka. So in this question, we want to calculate the pH of a 0.3 molar solution of acetic acid. And here's the equilibrium for that. I've got acetic acid reacting with water to form hydronium and acetate. So we're going to start the same place we always start. We're going to start with, what's that expression look like? Well, the concentration of hydronium times the concentration of acetate, right? Products over reactants. We ignore water because it's a liquid, so be over the concentration of acetic acid. So we know the Ka for acetic acid. It's 1.8 times 10 to the minus 5. We know the initial concentration of acetic acid. We want to find pH. And to find pH, this is our unknown. We need to find what is the hydronium ion concentration for this solution at this concentration and at this temperature. So again, we can break this down into an ice table. We know initially I have 0.3 molar acetic acid. And I know the Ka for this is 1.8 times 10 to the minus 5. So how can I put this information together to determine the pH of this solution? So for this reaction, we know the only source of hydronium and the only source of acetate is from acetic acid. And again, we have the 1-to-1 ratio. So for every 1 hydronium I form, I will also form an equal amount, and I'll have an equal concentration of acetate. So I'm going to gain plus X of hydronium and the same amount of acetate. We can make the same assumption because this is a weak acid. We can say that there's going to be such a small concentration of this that actually ionizes that our initial concentration will be very equal to our equilibrium concentration. They'll have 0 change in concentration. So a 0.3 will be our concentration at equilibrium as well. So here's our equilibrium expression for this acid, right? Ka equals the concentration of hydronium times the concentration of acetate all over the concentration of acetic acid. And we know that value of Ka is 1.8 times 10 to the minus 5. So we've got 1.8 times 10 to the minus 5. We're going to plug in what we know. Well, the concentration of hydronium is X, the concentration of acetate is X, all over the concentration of acetic acid, which is 0.3. So multiply that 0.3 across, right? Multiply both sides by 0.3, and we get 5.44 times 10 to the minus 6 equals X squared. Well, now we just take the square root of both sides, right? So I've got X squared equals 5.44 times 10 to the minus 6. I'm going to take the square root of both sides to see that X equals 2.32 times 10 to the minus 3. What is X? People always get lost at this step because you do so much math, you forgot where and how and why you started the problem. Well, X is my concentration of hydronium, right? That's what I need to determine the pH of the solution. So the last step, pH equals the negative log of hydronium ion concentration. The pH of this solution equals the negative log of 2.32 times 10 to the minus 3. The pH of this solution is 2.63. And again, we set this up and got this going by using the balanced chemical equation and the coefficients from those equations that let us know that I should have equal concentrations of hydronium and the conjugate base acetate because of the balanced equation. They're formed in equal number, equal ratio, equal concentration. From there, we're able to determine the concentration of hydronium and then ultimately the pH of the solution. We can also determine the percent ionization for this acid, remembering that percent ionization equals the concentration of hydronium all over the concentration of my weak acid HA times 100. So the concentration of hydronium that I determined in the previous reaction, 2.32 times 10 to the minus 3, all over my initial concentration of the acid, which was 0.3 multiplied by 100, and approximately 0.77% of that acid is ionized. And so, what that means is for that equilibrium, for the acetic acid reacting with water to form the hydronium and the acetate, right? Really, the reverse reaction is much larger than the forward reaction because that means of the material I added to solution, about 99% is over here as a molecule of acetic acid in solution, and only, less than 1% is over here as hydronium in solution. 0.77% is actually ionized in solution. So yes, that equilibrium falls on the left. Yes, that is a weak acid. There's one group of acids that we haven't talked about, and I'm only going to just mention it briefly. We won't spend too much time on it, and those are polyprotic acids. Polyprotic acids are acids that have more than one acidic proton. Because they have multiple acidic protons, they have multiple Ka values, where each Ka is associated to one specific proton on that molecule. So examples, right, are ascorbic acid or citric acid. They are polyprotic acids because they have multiple acidic acids. But you'll notice that the Ka values are drastically different. Just looking at ascorbic acid, for example, the Ka for the first proton is 8 times 10 to the minus 3. The second proton is 1.6 times 10 to the minus 12. That second ionization is incredibly small. It's much smaller than the first initial ionization because it's harder to remove each successive proton from that acid. So the first proton lost is the most acidic proton. Each proton after that is going to have a smaller and smaller and smaller Ka value because it's a weaker and weaker and less acidic proton. So if you have to calculate the pH for a polyprotic acid, the majority of the time, any calculation I would give you you are safe in using the first ionization, the first equilibrium constant for that polyprotic acid in determining the pH of that solution.